Okay, Bismillahirrahmanirrahim. Let's start our class. So, in the previous class, we have started the transformer protection. So, in the previous class, we have uh, briefly discussed the the in the previous class we briefly discussed the faults in the transformer, the incipient fault, which are also called as the minor fault, and the second one are the non-electrical fault. Okay, so and then we have discussed the reasons for the occurrence of these faults, the leakage of oil, second, deterioration of the quality of oil, and the third reason for these faults were failure of cooling system, and the fourth one was inter-turn fault. Then we have discussed the Buckles relay, and then we have discussed that the Buckles relay have some limited application against the incipient fault. Okay, so now with this background, we will further move our lecture for the transformer protection. Okay, so uh, now with this background, uh, let us consider the second type of fault uh, that occur inside the winding of the transformer and the core of the transformer. So this fault are known as internal faults. Okay, or these are also called as electrical fault that occur in the transformer. So now the first type of the protection we provide against the terminal fault in the transformer, and a terminal fault in the transformer, that is known as the overcurrent protection. Okay, so now we know that there are different, if we classified the transformer, uh, mm, so transformer can be classified as a power transformer and the distribution transformer. Okay, so whenever the cost of the differential relays, because normally we use the differential relays in the power transformer for the protection against any type of short circuit. However, when we use the distribution transformer, the cost of the distribution transformer itself is not that comparable with the power transformer. So differential relay cost is also very high. So we use the differential relay only for the protection against short circuits uh, in case of power transformer. But when we go for distribution transformer, then we cannot use the differential relay. Okay, that's the difference, because I have told you earlier that we have to use a particular protective device only when the cost of that particular protective device is almost 10 to 15% of the cost of the equipment to be protected. Okay, so that point should be noted. So in this case, when we have a condition like when we use distribution transformer, then and we need to protect that against short circuit, then we need to go for the other we need to go for the other type of the protection other than the differential protection. So far that we will go for the over current protection. Okay, and for the over current protection, as you can see in the slide, I have shown this figure, uh, that is the delta star transformer. Okay, so delta and star transformer. So it is a three-phase diagram, and this is a dy1 connection, delta star dy, delta y connection, or delta star connection. Okay, so this is dy1 connection. Okay, now we can see that On the delta side of the transformer, uh, this side I have connected the three CTs. This is CT1, CT2, and CT3. Okay, on the delta side. So these are the three lines CTs. Each CT that is connected in one phase. Okay, so each CT is connected with one phase. This CT is with phase 1, second CT with phase 2, and third CT with phase 3. Okay, along with each secondary of the CT, the secondary side. This is the secondary side of the CT. I have connected the three overcurrent relays. These are OC, means overcurrent relays. So these overcurrent relays are connected to the secondary side of each CT. Okay. In Okay, one in each phase and one earth fault relay. Okay, this is one earth fault relay. So whenever any short circuit occurs on the delta side of the transformer, this is the delta side of the transformer, then these over current relays detect if magnitude of the current exceeds the pickup value. Okay, and hence it gives further signal so that it disconnect the circuit breaker. So keep in mind, such type of relays are used on the delta side of the transformer. Okay, so these are connected on the delta side. Similarly, we need to protect the star side. This is the star one, Y connection or the star connection of the transformer. Okay, so we need to protect this side also. So on this side we need to use some other protective device. Okay, this side. Again, this is only for the case where the cost of the protective device that is not very high. That means we cannot use the differential protection that is for distribution transformers. Okay, now let us consider. Okay, let us discuss the second type of the protection, that is known as restricted earth fault protection. Okay, now before we proceed such type of protection, we need to consider the concept of grounding first. Okay, now whenever we consider the star delta transformer, the star side, that is the HV side of the transformer, is always star connected. So if I consider the delta star transformer having connection 1, then the star side, this side, that is always the high voltage side, and the delta side, that is always the delta side always the low voltage side. Okay, so this is the star, the delta side and the star side. The delta side is what the low, and the star side is high. Okay. Okay, now what's the reason? The reason is that if I put the star side, that is the high voltage side of the transformer, then whatever voltage, phase voltage, that will be reduced under root 3 times with reference to the line voltage. Okay, according to, as you know, the formula of the star. Okay, so it will reduce the current by 2.707 times of the line current, of the line voltage. Okay, so if I phase current, if I consider on the delta side or the low voltage side winding, that is also reduced to under root 3. So this is the reason for the star delta power transformer. I always HV side is star connected and LV side is delta connected. Okay, so keep this point in the mind. Now if I further consider the star connected, that is HV side of the delta star transformer, then this on the star side, you can see there is a grounding point. the star side, okay, there is a grounding point. Okay, this is the HV side, and this is the LV side. Okay, so this star point that can be isolated or that can be connected solidly, or may be connected through some impedance. Okay, so there are there are many type of the grounding. You can connect it through impedance or some solid resistor. Okay, so if the neutral of the star connected delta star transformer is isolated, then this is not the common practice. This is not the common practice. It is never be isolated, because if it is isolated, then voltage, the voltage whenever fault occur on this side, say any line to ground fault occur somewhere here, for example, at this point. Okay, so the core fault, then healthy phase, that is R phase and Y phase voltage. Okay, this is the B. Okay, and when if the fault occur on this B side, okay, uh, core line B to core fault. Okay, if the fault is line to uh, phase to core fault, okay, then these two are the healthy phases, red and yellow. Then these healthy phases voltage, these voltage will become the line voltage, so the insulation requirement will increase. So hence this is never be isolated, so it is also always connected to ground. Now there are two options, whether the star connected, that is solidly grounded, or it is grounded through some impedance. Whenever it is grounded through some impedance, it is known as non-effectively earth system. Okay, look, HV winding is isolated or grounded to high impedance, and it is called as non-effectively earth, and the voltage of the healthy phases increases. Okay, these two are the healthy phases, so the voltage of these two phases will be increased. And when it is solidly grounded, okay, if this was the case of through the impedance, now if it is solidly grounded, then it is known as effectively earth system. Okay, so if I consider that the neutral is grounded through some high impedance, or when I consider the neutral solid ground, then each has certain advantages and disadvantages. If I consider the first case, when the neutral is solidly grounded, then the magnitude of the current is very high. But on the other side, if I consider the same case, then whenever any fault occurred somewhere here on the blue side, for example, on this side, then the healthy phase voltage, that is not going to increase to the line voltage, because when this transformer on right hand side of this transformer, this current is located in switchyard, and along with this the very high voltage transmission line are eliminating. So whenever isolators are provided on the switch yard for this transmission line, the insulation requirement is not restricted only up to this point, but is also applicable to the line insulator. So that is why this is always either solidly grounded or grounded through impedance. But if I consider the second case, that is grounded through some impedance, and if any fault occur, then the healthy phase voltage that may increase, and that depend okay, in the second case, when it is connected through some ground, some impedance, then if the fault occur, then the healthy phase voltage that may increase, that depend on the value of the reactor or resistor connected here in the ground. So if I consider, if I connect through this ground through some impedance, then of course, obviously the magnitude of the fault current reduces. But at the same time, whenever such this fault occur, the other two healthy voltages that will go up to 80% of the line voltage, and that is not restricted and only up to this HV point of the transformer. This, but as I told you, it is also applicable to the adjacent equipment, that is the line insulators for the line eliminating from the switchyard. So that is why, because to save the insulation requirement, this neutral, this star point of the HV side of the star delta transformer is always solidly grounded. The only disadvantage is whenever any fault occur, earth fault uh, on the star side, then the magnitude of the current will be very high. But any way that we can afford against the insulation requirement, which increases the cost. So to understand the restricted earth fault, this second one, to understand the restricted earth for the protection, let us consider the main important point, that is the necessity. Okay, necessity. This is the important point. Let us see first what is the necessity of the restricted earth fault protection. So, as I have told you, if any fault occur on the star side of the delta star transformer, then zero sequence current that is not reflected on the delta side of the transformer. So you can see in this slide, if any fault occur, ground fault or the earth fault occur, then whatever is the zero sequence current that is not reflected on this delta side. Okay, so if I use the differential protection, three CTs and three CTs will be connected on this side, and three CTs will also be connected on this side, this red, yellow, blue star side. And if I give the secondary current to the relay, then as this zero, okay, CTs on either side of the star, and if I give the secondary current to the relay, then this zero sequence current are not reflected or comes out of the delta winding. So differential protection that is not capable to detect such type of earth fault on the star side of the delta star transformer. So to protect this, uh, because different, as I have told you, differential protection is not that much sensitive. So we need separate protection for any fault, for detection of any fault on the R side of the delta star transformer. So for that restricted earth fault protection, that is used. So now let us consider how the restricted fault protection that is applied on the star delta transformer. Okay, this is because this is actually the power transformer, and this is the star delta transformer. Okay, restricted earth fault, REF. Okay, this is the actually the external fault. Now this type of scheme is known as REF scheme, that is restricted earth fault protection scheme. Again, if I consider the delta star one transformer, okay, the dy delta wire transformer. So LV side, that is the delta side connected. So you can see here, and the star side, this is the on this HV side. This star connected is solidly grounded. And if I again connected the three line cities, And if I have also used one neutral CT, and the secondary of this neutral CT, uh, okay, this is the neutral CT, and this is your these are the line CTs. So the these are the line CTs, and this is the neutral CT. So the secondary of three line CTs, these are the secondary side of three line CTs, and the neutral and the secondary of the neutral CT, that is connected at this common point. And at this point, between these 2 points, the relay, uh, okay, whatever we call, whether we use overcurrent or the differential type relay, that is connected along with some resistor RS. This resistance is known as stabilizing resistance. This type of resistance, stabilizing resistance, is connected in series with the relay or the relay coil, just to ensure that the relay should not operate in normal condition or when there is no earth fault. Okay, so this is a function of this stabilizing resistor RS. Okay, now let us consider the working of the restricted earth fault protection scheme. Okay, this is the external fault. First, the working is the case of external fault. So this is the external fault. Okay, so now this one. Okay, so now let us assume that one fault occurred somewhere here. This is the somewhere, the fault occur somewhere here. Okay, this is the external part. So whenever such type of fault occur, you can see that the direction of the fault current on the primary of this CT, this is like this. So secondary, okay, the current will be just like this. Okay, the current will be IF. So you can see that this current will flow like this. So as the magnitude of the current through neutral CTs, so secondary side of this neutral CT, the current flow uh, in this direction. Okay, so the direction is like this. This current will flow in this direction. So you can see that in this fault on this side, which is the external fault, uh, no current that flows through the relay, and hence relay will remain in stable condition. It does not operate. Now if I consider the second case, that is the internal fault, that is somewhere, for example here, the fault occur over here. This is the internal fault inside the winding of the ground. Then you can see that the direction of the fault current will be, okay, the direction of the fault current will, so you can see that the direction is from this point here to the fault point. Okay, to this ground, then back, then come back. So you can see that as the direction is like this, the current fault current flows only through the neutral CT. Whereas in earlier case, the fault current flows through the neutral CT. So you can see here as so here as the fault current flows through the neutral CT. So this secondary of the neutral CT, small IF current will flow. Okay, this current will flow through the relay, and if this current exceeds the pickup value or the setting value of the relay, then this relay will operate. Now, with this discussion, the third type of the protection that is known as the differential protection. Okay, this is the case for the external fault, and this is the case for the internal fault. Okay, now the differential protection for the power transformer. So differential protection that is widely used for the protection against the short circuit in case of power transformer. So in this case, this is used only in the case of the power transformer whose rating that is normally how much above 1 MVA. Okay, above roughly about 1 MVA means high rating transformer. Maybe you can use such type of differential protection. Now that whenever we apply differential protection to the transformer, then few things or the few factors we need to be considered. So first, let us discuss how we can apply such type of protection. So you can see here, this is the transformer. Okay, this one is the transformer, which we need to protect the winding of the transformer. Okay, and on each side of this winding of transformer, I have connected the CT, the CT1, CT2, and the secondary side of the CT1 and CT2 that is given here. Okay, these two are CT1 and CT2 on each side of the transformer winding. And at this point the relay is connected. Okay, the relay is connected at this point. This is known as what type of relay? The differential relay. Okay, the standard number of this protection relay is 87. So whenever you apply such type of differential protection, you can see that the volt ampere on either side, LV side and HV side, are equal. Whenever the voltage ratio and the current ratio is different, so whenever you apply such type of differential protection, you have to apply like this, and you can have to ensure that this relay should not operate in any external fault. It operates only in the case of internal fault in the transformer or the core of the transformer. Okay, now the first type of the differential protection that is known as circulating current differential protection, as you can see in this slide. So I have shown here the diagram that is the winding to be protected. Okay, these are the winding to be protected. That is it is only a single okay, it is only a single line diagram so far. Only one phase is considered. So here the winding of the transformer I have shown. I have connected the two CTs, CT1 and CT2 here, and the current through CT1 is capital I1, and which is primary side, and secondary side of C2, that is capital I2. Again, when you transfer this current, uh, okay, to the secondary side of it is small I1 and small I2. Okay, small I1 and small I2, and you can see that this current that will flow here, the capital I1 and the capital I2, these are 180 degree. Okay, the capital I1 and small I1 are 180 degree phase shift. So the current that flows, that is like this, and the point A and B. Okay, this is point A, which is connected over here, and this is point B, which is connected over here. So between these two, point A and B, I have connected the relay. Okay, and through this relay the current flows, that is the I1 minus I2. Okay, so I1 minus I2, or you can also say I2 minus I1. So it is I1 minus I2. Let us take the absolute value. So the absolute value of this will be 0. Okay, now let us consider faults F1 occur, which is the external fault, and the other is known as F2 fault, that is inside the winding of the transformer. So we can say that it is the internal fault. Okay, so how the circulating current differential protection scheme works in these two faults. The principle is it works on the Kirchhoff's current law, means KCL. Current entering to the winding of the transformer, that is capital I1, and the current leaving to that winding, that is capital C2, uh, the capital I2, these current will be compared. I1 and I2 will be compared. If these two currents are equal, then there is no internal fault path exist, and hence this indicates the normal condition or the external path. However, these two currents are not equal. There is a significant difference is there between the capital I1 and capital I2, or similarly the small I1 and small I2 that flows the relay. Then means these two current will flow through the relay. Then obviously some internal path exists, and relay has to take care of this. Okay, so you can see that in case of external fault, this is the external fault, the small I1 and the small I2 are equal. Okay, so the difference of I1, capital I1 minus I1 minus I2, that is the ideally it is 0. So the 0 current will flow through the relay, means no current will flow through the relay. So whereas in case of internal fault, that is F2, so then I1 and I2 are not equal. Okay, the difference of I1 minus I2, that is a significant, and if it exceeds some value, say pickup value or the plug setting of the relay, then the relay will have to operate in this case. So ideally this current should be 0 when there is no fault or no external fault. However, it is not possibly possible practically. So why this is not possible? Because of the two reasons. Okay, this the difference of these two current is not ideally is not practically zero, but ideally zero. So what's the reason behind of this non-zero value in practical case? So there are two reasons. Okay, so one, whenever you apply circulating current, differential protection scheme, or any differential protection scheme, polarity of the CT, that is very important. If the polarity of the CT is not maintained, then instead of I1 minus I2, differential current that flows through the relay. The addition of these two current I1 plus I2 uh, and hence relay will operate, and it is actually the mal operation in normal or external fault condition. So first point is the polarity of the CT, that is very important. Okay, the polarity of the CT, otherwise the mal operation of the relay will occur. And the second important point, that is we know that the equipment to be protected here is the transformer. So transformer and the CT both are located in the switch yard. So whenever where is the protective devices, that is the differential relay, these are related are located in the control room. Okay, so this CT and the protected winding transformer both are in the switch yard, whereas the relay is located in the control room or installed in some control panel inside the room. So you need to run the wires from CT winding to this point. Okay. And here again from CT secondary to point A, these wires are that is going to carry the current, small current I1 and small I2. Okay. Small current I1 and small current I2. This is the CT secondary current. So these wires are known as pilot wires. Okay, these two are the pilot wires, and whatever current that flows through these pilot wires, that is known as pilot current. So keep it in mind that this relay that is located at equal potential, that means this point left hand side of the CT1, okay, to the point A, and the secondary side, if voltage drop here and the voltage drop on this side from point A to CT of the secondary side are equal, then we can say that the differential current, that is ideally zero, means this I1 and I2 or this side. Okay, if these two current are equal, then we will say that the current flowing through the differential relay will be equal to zero. But practically these two are not zero. So the voltage drops are not equal because the lead length, when you run the secondary CT secondary wires from CT secondary to the relay point, these two lead length are not equal. So voltage drop are not equal. Hence this I1 minus I2 current that flows through the relay, that is not practically zero. Okay, so and whenever okay, so and whenever in practical condition, whatever current flows through the relay, when there is no internal fault in normal or external fault condition, that is known as the fault current. Okay, this is called the spill current. this spill current that is not fault current, but that is normally flows because of the unequal lead length on the both side of the relay, because relay is never be located at equipotential point because of so many reasons. Okay, the third reason that is known as the non-ideal CT saturation characteristics. Even if we suppose if we purchase any CT1 and CT2, even from the same manufacturer, then also the two currents, that is the small I1 and small I2, are not equal even through the primary two currents, capital I1 and capital I2 are equal. Okay, hence because of this non-ideal CT saturations characteristics, the difference between the I1 and I2 that exists. So I1 minus I2 is not practically zero. So because of this, the sum current that is always flow through the operating coil of the relay, and this current is known as the spill current. Okay, so keep it in mind, the value of the spill current that is very high in case of the external fault. So whenever we apply such type of protection in actual field, then spill current that is never be avoided. Okay, so this is mainly because of the, okay, uh, this is mainly because of the non-ideal CT saturation characteristics. Okay, this is the point number one. And the second is because of the unequal lead lengths. This is reason two. So spill current is always there, and if we wish to avoid this, the remedy, we cannot use the circulating current differential protection. Hence, we have to use another type of protection that is known as bias differential protection. Okay, so that is enough for this class. So let's review. We have discussed in this two type of the fault that occur in the transformer. One is the incipient fault, and the second one is known as electrical fault or internal fault that occurs in the winding and the core of the transformer. Incipient fault are, again, we have to use a Beckles relay for the protection against such type of mechanical fault. It is also known as mechanical fault. So whereas for electrical fault, we have to use a differential relay if we go for a power transformer, and we have to use some overcurrent relay if we apply it for distribution transformer. Okay, so we will continue this in the next class. So that is all for today. Thank you.